Okay, so let's do this new section, stretch and rotation. Okay, so then in the relation, I think before that maybe I should discuss this one. This spectral representation. I think I have some note. Uh, yeah, here I have some note. Let's see. No. Is this another thing? Let me see. I think, okay, this is another thing. Okay, here we do stretch and rotation. So we have this F matrix, which is like this, and small f matrix like this, right? And this actually means this one in more detailed form. This is partial xi, partial large x alpha. Okay. So then we make a transpose of this matrix. Then we multiply dx. So this gives this one. I think you can imagine this without much difficulty. So this one, you can, this is like, how do you say, this is more like this. If you consider one component, this is partial x1 partial, no, I'm sorry, this is x alpha, small xi, then dx1, let's do this one, this partial large x alpha, small x2 dx2, partial plus large x alpha, small x3 dx3. This is same thing. This thing is same thing as this. Yeah. So then, if you have all component, you will obtain this compact form. This form and this form. Okay. Using the polar decomposition, we get F transpose was actually this. Do you remember this? F transpose? Ah, I don't know why do I have this sound. Is a message from Professor No. Okay, anyway, let me look at it later. So F is like this. F is VR. F is VR. F equal VR or RU. and transpose F transpose equal U R transpose. U is symmetric. So it doesn't change. Or this is also F transpose. And the same apply to small u, small r transpose, which is F transpose, and R transpose V, which is also F transpose. The operation on X, on dx, show that in the first case, the material element is rotated by R transpose and then stretched by U. In the second case, it is first stretched by V and then rotated U transpose, R transpose. For arbitrary unit vector n equal dx divided by ds, we obtain dx equal R transpose V dn ds, V n ds, writing small n unit vector is dx divided ds in small letter. We have small n unit vector equal d large S divided by d small s R transpose Vn. Okay, then if n equal eigenvalue of G. Okay, if this is eigenvalue, if this is eigenvalue of G, we will get this. So I have some note for this. Let's see. So here is a note. Yeah. So we have G. I'm sorry, I cannot write on top of this image. So I just use a cursor like this. So this is a matrix. Yeah, this is matrix multiplied by this. This is vector equal some eigenvalue multiplied by vector. Okay, so this vector is eigenvector, and G gamma is eigenvalue, and G is matrix. And this G matrix is given by F times F transpose, which is using spectral decomposition, polar decomposition or spectral decomposition, polar decomposition maybe. So VR times R transpose V transpose, so which goes like VV transpose, and V matrix here is actually a symmetric matrix. So we can write this V square, okay? And G in spectral form, spectral representation, we can write it here. There's a diagonal matrix with eigenvalues, 3 eigenvalues in diagonal place. Then we have this orthogonal matrix. I think it's called orthogonal matrix. In quantum mechanics, it's called unitary matrix. So, and it's called unitary transformation. Anyway, so then this diagonal part actually can be written as lambda square. Okay, each of G1, G2, G3 are lambda 1 square, lambda 2 square, lambda 3 square. So you can write this as this lambda diagonal matrix square. Okay, then if you uh, perform this multiplication, you will obtain a lambda square in diagonal places. Yeah? So then actually you can separate this power 2 like in this way. So one of the you keep u inverse, then you have just a lambda diagonal matrix, and you put u inverse. This is just identity matrix. Then you multiply another lambda diagonal matrix, and finally you put u. Then you cut into half. Okay? Then you will see this is like a V matrix times V matrix. Yeah, so each of them is V matrix. So then you can see, you can consider this V matrix times eigenvector. This eigenvector is eigenvector for G. So then V matrix looks like U inverse diagonal times U, which is multiplied by eigenvector n, right? Like this. Previous last time. This can be 100 or 010 or 000. This one you multiply by eigenvector, which become 100, 010, or 000. Okay, so that means this will pick one of these diagonal term. Okay, so if gamma is 1, you will pick lambda 1. If gamma is 2, you will pick lambda 2. Gamma is 3, you pick lambda 3. Okay, then the remaining part is u inverse times u times n. I think this is correct. See, this un is 100 or 010, 001. Then you just multiply such vector to this diagonal matrix. Then all you get is this one term, and the remaining vector is just the same as before, like un, which is 100 or 010 or 001. So then you will see there is a u inverse u, which is just identity matrix. So you get lambda gamma n. So this is like eigenvalue equation. So you get this V, which is a matrix, times eigenvector equal lambda gamma eigenvector. Yeah. Okay. So you have this. You have this. So you put this Vn to top. Is that right? I don't know. N is n gamma, right? So you obtain Vn. I'm a little bit confused. Okay, so this ds over ds ds over ds. This is 1 over lambda. I think I can write it. This is lambda gamma 1 over lambda gamma. Right? So you can, if you put here, you put lambda gamma and gamma. Then you can cancel this and this. Yeah. So what is left is RT times n gamma. This one. So this small n is RT n gamma. Small n is RT, R transpose large n gamma. Thus, the unit vector along a, sorry, I have to. Thus, the unit vector along a principal direction undergoes a rigid body rotation. A triad of mutually orthogonal unit vectors representing the three principal directions will get transformed to a new triad of orthogonal unit vectors. Okay. Using F goes RT R transpose V inverse. See, this is crazy. So we have this one. Let me see. FF equal I. So we have FF equal I. So F, small f, is F inverse. Right? So then F inverse is VR inverse. VR inverse. This is like R inverse, V inverse. Then R inverse is R transpose because this is orthogonal matrix. Then you have V inverse. So G is actually G is F transpose. I think G is FF transpose, right? We should see it somewhere. This one, this is G. G is FF transpose. And then F transpose. F transpose is V inverse transpose R. Okay, so then V is symmetric. V is a symmetric matrix. So then that means V inverse is also symmetric. So you don't need transpose anymore. So you multiply F times F inverse, which is G, No, I'm sorry. F transpose. G is F transpose, and F transpose is V inverse R. F is RT transpose V inverse. So you multiply RT V inverse times V inverse R. So you obtain RT V inverse square R. So then you multiply N, Gn. You make Gn, so RT V to the power 2, power minus 2, R, then this part is from this N. So you have, what is this complication? R transpose V, think R transpose, this is R inverse, so this is identity. So you can see this is identity. This part is identity matrix. So then you have V square N. And this is not so clear, but you obtain this one. So I don't know. I don't think this is so straightforward from here. Not so straightforward. V inverse N gamma goes like lambda gamma 1 over lambda gamma N gamma. This is not so straightforward, but if you admit this relation, you have, look at this V inverse square multiplied by eigenvector. So you have 1 over eigenvalue square in front. Then you have RT. Then this RT n, large n, this is small n. Crazy, huh? It's crazy, kind of crazy. So G inverse, Gn is lambda. See, this is more like a eigenvalue equation. This is lambda gamma square n. What we have before was this G, large G, large N is lambda gamma square N. This is like gamma. Yeah. Okay, so thus small n is the eigenvector of G, small g, and the new triad just mentioned points along the principal direction. And the new triad just mentioned points along the principal directions of material ellipsoid of Cauchy. What is a material ellipsoid? See, what was the material ellipsoid? This is spatial ellipsoid. Material ellipsoid is this one. This is material ellipsoid. And this is spatial ellipsoid. See, what looks like material sphere is actually material ellipsoid, and what looks like spatial sphere is spatial ellipsoid. Okay, so it's opposite. The definition of the word is opposite to the feeling we have. So you can see material. This is the material sphere. Okay, material ellipsoid or Cauchy is more like a material sphere. So this is sphere in material uh, material coordinate. So principal. So this will go to ellipsoid. If you go to spatial coordinate, this go to ellipsoid, right? So then this principal axis, that's n. That's here. This is this principal direction of the material ellipsoid of Cauchy. Also, the largest major axis of the spatial ellipsoid. Spatial ellipsoid. The spatial ellipsoid is sphere in spatial coordinate, mapped into the smallest semi-major axis of the material ellipsoid. This is a material spatial ellipsoid. This is also special. So this will get mapped to this spatial ellipsoid. Why do they say material ellipsoid? This is like I would say spatial ellipsoid in material coordinate. So strange. spatial ellipsoid gets mapped into the smallest semi-major axis of the spatial ellipsoid in material coordinate. I think spatial ellipsoid in spatial coordinate is sphere, right? Spatial ellipsoid in material coordinate is ellipsoid. Material material ellipsoid in material coordinate is sphere. And material ellipsoid in spatial coordinate is ellipsoid. Do you agree? I don't know. I hope I'm not wrong. I hope I'm not wrong. So let me see. Let me write it down. let me type. So spatial ellipsoid. This is spatial ellipsoid and material ellipsoid. Spatial ellipsoid. Strange. Spatial ellipsoid and material ellipsoid, right? So then you have, see, I write this way. I just do this way, and this way, right? And we have material coordinate. And spatial coordinate. Then we have sphere. Sphere ellipsoid. Ellipsoid ellipsoid. So spatial ellipsoid in spatial coordinate is a sphere. Yes, material ellipsoid in material coordinate is a sphere. Okay, so spatial ellipsoid in material coordinate is ellipsoid. Yeah. Material ellipsoid in spatial coordinate is ellipsoid. This is what I think. Am I correct? So what I say is here. Semi-major. See, let me see. Let me delete this. Delete this. Let me. Material ellipsoid of Cauchy. Okay, so then I would say, this is what I can say. Here, this is large N. For material coordinate, we use large N. Then for spatial coordinate, we use small n. Yeah. So n is the eigenvector of G, and new triad just mentioned points along the principal direction of material ellipsoid of Cauchy. Material ellipsoid of Cauchy. Is this one? This one? Also, largest semi-major axis of a spatial ellipsoid. I got confused. えーっと、I think we consider only spatial. Let us concentrate on spatial ellipsoid. Okay, we consider spatial ellipsoid for the time being. Spatial ellipsoid. Okay, this is a spatial ellipsoid, and this is a spatial ellipsoid. Okay, let me see what page is this. 76. Spatial ellipsoid. The new triad. So confusing. Oh my god, it's a different page. Okay. Very strange. See, I think we consider spatial ellipsoid, right? So we have been considering spatial ellipsoid. We have been considering spatial ellipsoid. So this becomes ellipsoid. So then there is a principal axis which was called N. Ah, yeah. So now probably okay. You can just make this you consider sphere here, but the same n, we consider same n as this. Yeah. Then we go to this way. So then you have another ellipsoid, and you have like this n, and then this largest principal axis become the smallest principal axis, and smallest principal axis becomes the largest principal axis. Does it make sense? Thus, n is the eigenvector of small g, and the new triad just mentioned points along the principal directions of the material ellipsoid of Cauchy. largest semi-material major axis of the spatial ellipsoid gets mapped into smallest semi-major axis of the yeah, maybe that's the case. So you start with a sphere, spatial ellipsoid in spatial coordinate, which is a sphere. Then this goes to ellipsoid in material coordinate, which is called spatial ellipsoid. So then you obtain a major axis n, n1, n2, n3. So then you make a sphere in material coordinate. So here, if you make a sphere in material coordinate, which we call material ellipsoid, but in this sphere in material ellipsoid, a material coordinate, the major axis will be mapped to small n, which is material ellipsoid in spatial coordinate. So then this major axis of small n is a map from the minor axis of spatial ellipsoid in material coordinate. I think I hope this is correct. Okay, so I have some other plan today, so I have to stop this video here. Okay, so see you later.